Hi folks, we're going to take a look at number 10 from page 128. So they give us this position with respect to time function. So where position's in meters and t is in seconds. And the first question they ask us is to calculate the object's velocity and acceleration at any time t. So essentially what we're looking for is a derivative and second derivative of the position function, because the velocity is just the rate of change of the position function. Okay, so that's just the derivative of that position function. So here, in order to find this derivative, the first thing I'm going to do is I'm going to distribute this out, because it'll be easier to then find the derivative than using the product rule. So this is going to become 7 times t to the 5 over 2 minus t to the, well, 5 over 2 plus 1 is just going to be 7 over 2. Okay, so I'm going to work with this form instead. Okay, and so here we just have 7 times 5 over 2 times t to the 3 over 2, okay, minus 7 over 2 t to the 5 over 2. Okay, so our final answer for the velocity is going to be 35 over 2 t to the 3 over 2 minus 7 over 2 t to the 5 over 2. Okay, and this now also puts us in a good position to determine the acceleration. Okay, so here the acceleration function is just the derivative of the velocity function, or the second derivative of the position function. Okay, so here we just have 35 over 2 times 3 over 2, so that's 105 over 4 times t to the 1/2 minus 7 times 5, 35 over 4 times t to the 3/2. Okay, so here are our velocity and acceleration functions. So let's see what they're asking for next. They say, after how many seconds does the object stop? Okay, so to be stopped means you're not moving, meaning the velocity needs to be equal to 0. So what we're solving for in B is we're solving for when the velocity is equal to 0. Okay, so 0 equals 35 over 2 t to the 3 over 2 minus 7 over 2 t to the 5 over 2. Okay. Now we've seen something like this in an earlier problem. If you watch one of the other videos or you solve the problem yourself, we're going to use sort of the similar trick that you would use if you were factoring something that had integer exponents. So what I'm going to do is I'm going to factor out the power of t with the smaller exponent. Okay. Now I can also factor out some other stuff because they both have a common factor of 7 and 1/2. So I'll actually factor out the 7 over 2. Okay. So here I'm just going to be left, oh sorry, times, I said the highest power of t. So luckily that's made to look like a t. There we go. Okay, and what we're left with here is, well, we're still left with a factor of 5 in the numerator. Okay, but this whole thing and the 1/2, that's all been factored out. Minus, so no more 7 over 2, that's been factored out. And if I divide t to the 5 over 2 by t to the 3 over 2, well, I'm just left with 1. So that just ends up being 5 minus t. Okay, and so this is nice and easy to solve now. So here we have a solutions t equals 0 or t equals 5. Okay. Now here it says when it changes direction, but here if I look at t equals 0, well, that's just the initial. So that means it started off at a velocity of 0. Okay, but that's not what I'm interested in. I'm interested in once it started moving, when does it stop? So that happens at t equals 5 seconds. Okay, so now the next question says, when does the motion of the object change direction? Okay, so that means where does it go from moving, say, from the right, towards the right, to moving towards the left, or the other way around? Okay, and we know that the direction of motion is again given by the velocity. Okay, so what we need to figure out is when is this velocity positive and negative, and at what point does it change direction? Now, from B, you should, likely probably have an idea of when this is going to happen. But let's just take the velocity function here. Okay. Now we've already factored it out. Now first of all, I'm only interested in values greater than 0. Okay, and we see here that in order to determine the sign of a function, well, we just look for where it's either equal to 0 or doesn't exist. Those are the only places it can change sign. Well, here, this exists everywhere, so the only place it can be equal to 0 is at 0, which is my starting point, and at 5. Okay? So now, because the velocity is equal to 0 at 5, doesn't mean it has to change direction. Okay? So I could sort of come to a stop and then start moving in the same direction, or I could come to a stop and then move in the other direction. So I just have to check the sign of the velocity. Okay? So here, if we put t equals 1, okay, that whole thing is going to be positive. 5 minus 1 is positive. Whereas if I put t equals 6, that whole thing will still be positive, but 5 minus 6 is negative. Okay, so indeed changes direction at t equals 5 seconds. Okay, so why? Because it went from moving in a positive direction to moving in a negative direction at that moment. Okay, so let's move on to D. So D says, when is the acceleration positive? Okay, so now again I have my acceleration function, and I'm going to have to do the same thing. I'm going to have to determine where it's positive and negative. And you're going to see that I'm going to do something similar to what I did with the velocity. I'm just going to factor this out in a clever way. So here, for a of t, so first I look at the coefficients, and there's a common factor of 1 over 4. There's also a common factor of 35. So we've got the numerical factor of 35 over 4, and I'm going to do the same thing. I'm going to factor out the smallest power of t, so that's t to the 1/2. Okay, so what we're left with here, so we're just left with the 3 from the 105, nothing else, minus, so here the whole 35 over 4 is gone, and when I divide t to the 3/2 by t to the 1/2, I'm just left with t. Okay, so we see that the acceleration function, okay, can only change sign at 0, well, though that's the starting point, so it's not going to change sign there, or at 3. And here, if I test a value, t equals 1, positive, positive, okay, and if I put t equals 4, positive, negative. Okay, so that means the acceleration is positive if 0 less than t less than 3. Okay, and of course this should all be in seconds. Okay, so again, notice how we're using all the same tricks as we have in the past. Okay, this is why dealing with these functions being positive or negative is nice, because I get to reuse all the algebra that we learned in the previous course. Okay, and let's see what the last question is. When does the object return to its original position? Well, I guess the first thing we have to do is determine the original position. So the original position would occur when t is equal to 0. So let's go all the way back up here. And if we stick in t equals 0, well, we see that the original position was at 0. Okay, so what we have to do is we have to figure out when is it going to go back to 0. But this is pretty easy to do, because if I set now this original function to 0, okay, I don't even think I need to write it out. I can see that it's equal to 0 at 0, which was its starting position, okay, but it's also equal to 0 at 7. Okay, so here s at t is also equal to 0 when t is equal to 7 seconds. Okay, so that means it's returned to its original position at 7 seconds. Okay, so just a quick recap here. Okay, the conceptual part of this I don't think was too difficult. It was just sort of applying what we know about velocity and acceleration, okay, and what information it tells you. So for example, velocity being positive, one direction, being negative, other direction, stopped when the velocity is 0. But what's important here is some of the algebraic tools that we used. So we saw how we can factor these expressions that have non-integers.